Hi, Physics 1, Mr. Janowski again. Here is part 2 of the Chapter 10 slides. In the last part, we learned about all the different cousins to the linear quantities we learned earlier in the year. Basically, for every linear idea, there's an equivalent, not an equivalent, an analogous rotational cousin. So the cousin of x is theta, the cousin of v is omega, the cousin of a is alpha, and so forth and so forth. So let's keep going with that idea. So first, I have no idea if this is even still going on. I should talk to Mrs. Horvath about that. Certainly the dates aren't. But yeah, if you're a junior and you're interested in taking AP Biology next year, why not join that Google Classroom code right there, XFF366X. Yeah, see if that's still a thing. And you might also just contact Mrs. Horvath directly. Horvath, SHORVATH, at charterarts.org. If you have any questions about AP Biology for next year. So, there's a Kahoot you can play. We can't all play together because remote learning won't allow for that. Or maybe we could, I don't know. But we're not doing the Kahoot right now. So, yeah, if you want to, there's the Kahoot. Go to the slides, click to it. So here is a photo of a wheel. So take a look at this photo. See if you notice something unusual about it. So the unusual thing is there seems to be a lot more motion blur at the bottom, at the top of the wheel than there is at the bottom. So if you look at this at the bottom, you can see the little points of the spokes where the spoke connects to the rim are fairly sharp. And as you go higher and higher up the wheel, they get increasingly blurry until when you get all the way to the top, you can't even really see them at all. So this is just a regular photograph. There's no photoshopping going on here. So why is this? So in the axle's frame of reference, the wheel is spinning in place and the road is moving to the left of the velocity v. So what that means is if you were riding along next to this bike rider and you were on your own bike and you were going at the same speed and watching her ride along, you would be in the same frame of reference as the axle. Meaning, even though, in a sense, the whole bike and the rider, they're all moving, if you're going along right next to them at the same exact speed, it's going to seem like the bike is not moving. So if you look at the axle would look very sharp. So that would just be the point there. In class, in some of the sections we got to do this, I just held the one wheel and I just spun the wheel. And I wasn't moving relative to you, and neither was the axle, but the entire wheel was spinning. So, yeah, keep that in mind. So even though the axle's not moving in that frame of reference, every point along the outside of the wheel is moving. It's got what's called the tangential velocity. So a point at the top, if this rider is going to the right, a point at the top would be going this way. A point at the bottom would be going this way. A point here at the right would be going down. A point here at the left would be going up, and so forth. A point right here would be going this way. So that's what tangential velocity is. So in this frame of reference again, the axle's not moving, so the velocity of the axle would be 0, but every point along the outside of the wheel has its tangential velocity v. So now back to the picture of the photograph. Notice how this looks very different from the other photograph. In this photograph, the axle is very sharp in the center, and the spokes are fairly sharp at the center, and the spokes get blurrier and blurrier as you go out. So that's how this photo works. Compare that to this photo. Again, in this one, it's sharp at the bottom and it gets blurrier going up. In the other photo, it was sharp in the center and gets blurrier going out. This one, sharp at the bottom, blurrier going up. So why is this? In this photo, the photographer was in the same frame of reference as the bike rider. So the photographer was rolling along at exactly the same speed as the bike. Probably not. There's a different way to take this photo, but let's go with that. So yeah, photographer in the same frame of reference as the axle. This one's different. In this case, the wheel just rolled by and the photographer was just sitting on the ground next to it. So if this wheel's going to the right, you can't tell from the photo which way the wheel's actually going, but if the wheel were going to the right, the whole wheel would have its velocity v to the right. And then you have to superimpose on top of that the tangential velocity that every other point of the wheel also has. So remember, looking at this picture, if the axle is not moving, but the whole wheel is spinning, the top has velocity v, the bottom has velocity v in the other direction. Now, the wheel is still spinning in this picture, and the whole wheel is moving to the right with the velocity of v, so you have to add those. So at the top, it had tangential velocity v to the right. It also has what you would call translational velocity v to the right. So the net velocity at this point is 2v. So it's moving very fast. There's a lot of motion blur up here. You can't even see the spokes. In the middle, the translational velocity is v, and the tangential velocity, well, it's 0. There's no tangential velocity at the middle. This is the point the whole thing's rolling around. So the net velocity here is just v. So there's still some motion blur, but less than at the top. Looks a little bit sharper here. Finally, you get to the bottom. So at the bottom, you have tangential velocity going to the left, but you also have its own regular translational velocity going to the right. So you add those like vectors, and you get 0 net velocity at that point right there. So kind of the weird thing about this, if you're standing by the side of the road and you see a car go by, okay, the whole car is driving by you at a velocity of v. If you look at the tires, the axle of each of the wheels, that's going at a velocity of v, the same velocity as the rest of the car. A point at the top of the tire is actually going twice the velocity of the car because the whole thing's moving to the right. And in addition to that, the wheel is spinning with a velocity of v at the outside. And then the weird part is at the bottom. The part of the tire that touches the road is just for an instant not actually moving relative to you, which I always thought was kind of neat. So yeah, you have the regular velocity, the translational velocity v to the right, but that's exactly canceled out by the tangential velocity of the wheel, which at this point is going to the left. Which is the point of this picture here. So now we understand that picture. So to compare them again, yeah, in the axle's frame of reference, look, very sharp in the middle, gets blurrier as you go to the outside. If you're in the frame of reference of the ground, so you're standing on the ground and just watching the wheel roll by, in this picture, it's very sharp at the bottom because this point isn't actually moving relative to you, the photographer, but then it gets blurrier as it goes up. So hopefully that helps. And the first time we did this in class, at this point, we started to go over the test, so this was a fairly short video. I hope. I don't actually have the running clock here. Either way, hope it helps.